Here are the main ideas on forces. The biggest thing about forces is that forces cause accelerations. And remember that an acceleration is any change in the velocity of an object. And remember that velocity is speed and direction. The units that we use for force are called newtons, not to be confused with fig newtons. Some commonly used forces. A way to remember those forces is we can use the phrase get to know all forces. And each letter stands for a force. Remember that G is for gravity. And that's if you're on or near a planet. And the direction of the gravity force is always towards the center of that planet. T is for tension. And you can think if there are any ropes or strings, and it's along the string away from the object. Then there's the normal force, and that's if you're touching anything. And the direction of the normal force is perpendicular to the surface, but away from the surface. We have applied force, which is any other push or pull on the object, and it would be in the direction of that push or pull. And we also have friction, which is if there's any sliding or trying to slide from the object. And the direction is the opposing direction of the local motion. And what we mean by local motion is the motion in the direction opposite, or where the two surfaces touch. And remember, with that applied force, you don't want to count any force twice. So if someone's pushing on something, you could say that they're touching, but then just count that as applied. Only count it as one thing. Next, we'd like to go into Newton's 3 laws. Newton's first law is that mainly objects want to keep doing what they're doing. Oftentimes you'll see this as objects in motion will remain in motion, but mainly they just want to keep doing what they're doing. Sometimes this is referred to as the law of inertia, and remember that inertia is a resistance to change. Newton's second law we can sum up as the sum of the forces equals mass times acceleration. And the idea would be that if we have some force on a big mass, it would have a small acceleration, and a force on a small mass would cause a large acceleration. And if we wanted to, we could determine the acceleration of an object by taking the force on that object divided by its mass. Some of the forces, that Greek letter sigma, is also referred to as the net force, and that means to add up the forces. And we need to subtract the force if it's hurting the motion of the object. If the sum of the forces is equal to 0, we know that it's not accelerating, but the object could be moving at a constant speed. Newton's second law doesn't tell us about the motion of the object, just the acceleration of the object. So if a cart is rolling along and someone is pushing it, and there's friction, and if those forces are equal and opposite, there will be no net force, but the cart is moving, it's just not accelerating. Newton's third law states that forces come in equal and opposite pairs. So with this, we could have a baseball hitting a bat, and the force of the baseball on the bat is the same as the bat on the ball. Oftentimes people think that the bat hits the ball harder, but they're equal and opposite. Or if you're driving along and you hit a bug, the force that the car hits the bug is equal to the force that the bug hits on the car. A way to kind of help understand that this is possible is think about the object with the bigger mass has less acceleration, and the object with the smaller mass has more acceleration. Let's take a look at drawing some free body diagrams. So if we have a box, we would have some gravity force because it's on or near a planet. We would have normal force pointing up, and let's give wheels on this thing so there is no friction. And then what we can see is that the normal force and the gravitational force don't line up. So we want to draw a dashed line in the direction of the acceleration. And then what we need to do is tip this so that the acceleration is in the x direction. That makes solving these problems a lot easier. Then by doing that, we do the sum of the forces in the x as mass times acceleration. The normal force points straight up, so it's not in the x at all. Gravity points in the x, but it's also in the x and the y, so we just want the x part. So we would use cosine to get the x part of the gravitational force. We do cosine of the angle between the gravitational force and the acceleration, which is the angle between the gravitational force and the ramp, which is not the angle of the ramp. It's actually 90 minus theta. So we use that for our cosine of the angle. And then the gravitational force is equal to little m, little g, and the masses end up canceling out. And this is the process you could use to get to acceleration. Friction affects motion. So if we have a cart with no friction and you apply a force to it, the cart's going to accelerate. But if we have a box on the ground and you apply a force to it and there's friction, the box might actually stay in place. You might not be able to overcome friction, or if you do, it's not going to accelerate as quickly as if it were on wheels. Remember, there are two types of friction. There's static friction, when an object is not moving. I like to think that it sticks or started, has that ST blend at the beginning. And we have kinetic friction. And that's when the surfaces are sliding against each other and there's movement between the surfaces of contact. This is an area that there's sometimes confusion, because if a car is driving, you would think, oh, it's moving, so it's kinetic friction. But again, we're looking at the local motion. The car is moving, but the wheels grip, so it's going to be static friction. And remember that static friction has to be greater than kinetic friction. If not, you would have some weird situations where you might be strong enough to start pushing a box, but not strong enough to keep it moving. And in reality, you might not be able to get it going, but if someone helps you with an initial shove, you'd be able to slide it along and get it to move. If we have a problem with multiple objects, example would be an Atwood's machine, where we have a pulley with two masses over it. And let's say in this case, mass 1 is greater than mass 2. And if we're looking for the acceleration, we would look at mass 1 and do sum of the forces equals ma. And the forces on mass 1, we'd have tension up and gravity down. And on mass 2, we have tension up and gravity down. For mass 1, it's a heavier mass, so it's going to fall down. So gravity's winning, and we do gravity minus tension equals ma. For mass 2, it's the lighter mass, so tension is winning, so we do tension minus gravity equals ma. And at this point, we could do substitution or elimination, and then we'd have all the values, so we could solve for the acceleration of the system. Remember, if the masses are equal, then the forces will be equal. And if the forces are equal, there's no acceleration. So if this starts at rest, there will be no motion. It'll stay where it is. Oftentimes, again, people think it'll level out, but it'll just stay in the position that it's at. And lastly, just remember that forces are vectors and the direction matters. We touched upon this on the ramp angle, but here's another one where we say, if in this case, the forces are equal in the x, which force is greater? Well, we look at the orange, and the orange has an x and y component. So the x part is equal to the blue, but it has that extra y component. And remember, we could do with the Pythagorean theorem to find out what the orange value is. But again, since the orange is also in the y, it will have a greater force, or it would have to be more of a force than the blue. So to wrap this up, again, remember the main idea of all this is that unbalanced forces cause a change in the motion of an object, which we call acceleration.